Turbulent flow. This one's going to have a much larger head loss than laminar flow because the particle motion is much more random. However, because the particle motion is so random and everything is all churned up, the average velocity and the maximum velocity are really close. Now there's more head loss, but through research and experimentation, we find that even with turbulent flow, we can still use the head loss equation of the Darcy friction factor times the ratio of length over the hydraulic diameter, velocity squared over 2g. Where it's going to change with turbulent flow is this friction factor, F. With laminar flow, it was that lovely 64 over the Reynolds number. With turbulent flow, we're going to need to use the Moody diagram. With the pipe surface roughness and the diameter, we can put these together for a relative roughness. And that relative roughness value we use with the Reynolds number in the Moody diagram. From the Moody diagram, we can extract our friction factor, F. So here it is, the Moody diagram. The relative roughness factor you can find in your end papers of your textbook on the back cover. So there's the relative roughness factors in your textbook. You'll see here that we've got the laminar flow. Okay, so that's around that 2,000 to 3,000 Reynolds number that we were talking about. Then we have the critical zone that's somewhere in between fully turbulent or fully laminar flow. And then we have this whole bit here that is the fully turbulent flow. Now what we do, ladies and gentlemen, is we calculate the relative roughness, and that's the line that we pick. And then we follow that line until we get to our Reynolds number. And then that's going to give us the friction factor at that intersection. So when the line curves, we curve with it. Yes, we can linearly interpolate between lines and do our best guess. This whole friction factor for turbulent flow is a best guess anyway, because that relative roughness is for new pipes. So if we have a new aluminum pipe versus one that's slightly corroded or has some buildup or scaling within the pipe, that's going to change the friction factor, but we can get a best guess from the Moody diagram. We can also use the friction formula that's Colby, Brooke White, and Swami Jan. I'm way off on that. Anyway, where the friction factor, and I'm going to write the denominator first, is the log of the relative roughness divided by 0.37. So epsilon d divided by 0.37 plus 5.74 over the Reynolds number raised to the 0.9. And this whole quantity is squared divided into 0.25. This gets us similar predictions to the Moody diagram, but again, because we've got so many factors in play for turbulent flow and the age of the pipe and the interior of the pipe, all of these are pretty best guess at best. So we've got a pipeline that's made out of commercial steel, has a diameter of 15 centimeters, and has 2 points that are a kilometer apart, A and B. Point B is 20 meters higher in elevation than point A, and the flow of the oil through the system is 0.03 meters cubed per second. We have a measured pressure at B of 300 kilopascals, and we want to find the pressure at A. Sounds to me like this is an energy equation. Setting up my 2 points, A and B, I'm going to set my datum at A. So that elevation will be 0. I don't have a pump. I don't have a turbine. And with a constant diameter and a incompressible flow, velocity A and velocity B are going to be the same. I was given my pressure at B. I was given my elevation at B. I was given my flow rate so I can solve for my velocity. The only thing I need to find is the head loss because now we know how to do that. Before we can find the head loss, we need to know, is it turbulent or laminar? We are going to do that with the Reynolds number, rho VD all over mu. Our density we can get with the specific gravity times the density of water. Velocity we can get by taking flow rate and dividing it by the area. So that's going to be the 0.03 meters cubed per second divided by pi over 4 times 0.15 meters squared. Get that centimeters to meters, and we find that our velocity through the system is 1.698 meters per second. We were given the diameter, we were given the viscosity, so our Reynolds number is 0.82 times 1,000 kilograms per meters cubed times velocity 1.698 meters per second times my diameter 0.15 meters all over the viscosity 10 to the minus 2 Newton seconds per meter squared. And we end up with a Reynolds number of 20,885. This is definitely turbulent. I have two ways to calculate the friction factor. I'm going to start with the Moody diagram. So with the Moody diagram, we need the Reynolds number that we already have. We just calculated that. And we need our relative roughness. So coming back to the roughness factors, we see here for commercial steel, we have a relative roughness of 0.05 millimeters. And we can put that over our diameter, which is 15 centimeters or 150 millimeters. And we have a relative roughness of 0.0003. On our Moody diagram, that's going to put us here between 0.0004 and 0.0002. So we're going to cruise along here. And we need 20,000. So that's 2 times 10 to the 4th. So somewhere in here. And it looks to me this is intersecting somewhere around 0.025. Yes, it's really that abstract because we're just trying to look at pictures and we're rounding and pulling these values, and that's about where it is. For those that want to try the friction factor equation, plugging everything into the equation, we get about 0.026. Again, like we said before, that's pretty close to what we get off the Moody diagram. With those friction factors, we can plug it into the head loss equation. I'm going to use the larger number because it's a more conservative head loss. And we have 1 kilometer over the diameter. And then that velocity we calculated earlier. all over 2 times gravity. We have a head loss of 25.5 meters. So we can plug that into what remains of our energy equation, and we find that the pressure at A is equal to 666 kilopascals. Let's say we're given this tank that has a water elevation of 60 meters and a pipe centerline elevation of 40 meters. The pipe diameter is 50 centimeters and it's made out of steel and is 100 meters long. What is the flow rate through the pipe? Again, I think I'm going to start with the energy equation because we don't have a velocity, so I don't have a velocity to multiply by the area. I am given an area of the pipe, but I don't have a velocity. So let's see if we can find one. If I set up the pipe as my datum and the tank as 1 and the outlet as 2, and notice that it's an open jet outlet. So open to the atmosphere, no pressure at 1, open jet, no pressure at 2. It's a tank, so there's no velocity at 1. I set 2 as my datum. I don't have a turbine, I don't have a pump. I do have head loss because it's 100 meters, and that's what we're talking about this lecture. And head loss is going to equal to my head loss equation, friction times LdV squared over 2G. I don't have F and I don't have V, but I can plug that equation in there and solve for velocity, which is going to end up being 392.4 over 1 plus 200 times whatever friction factor I have. And then I need to take the square root of that to get it in velocity. So now we have velocity in terms of friction, but I still don't have a friction factor. To get friction factor, I need the Moody diagram. To get a friction factor off the Moody diagram, I need a Reynolds number, rho VD over mu, or VD over nu, and I need the roughness factor E over D. Now this I actually have because I was told it was a steel pipe, so 0.045 millimeters over that diameter of 50 centimeters or 500 millimeters, but I don't have a velocity, so I don't have a Reynolds number, so I don't have a friction factor. So what I'm going to have to do, ladies and gentlemen, is guess. My relative roughness ends up being 0.12349. So if I go up to my Moody diagram, so my relative roughness is somewhere in here, okay? Again, remember we're trying to guesstimate to get a start. So it looks to me like a good starting value can be around here at this 0.015, okay? So it kind of gets us on the lower side of the Reynolds number and kind of in between my two values here. Just a starting point. So if we start with a friction factor of 0.015 that we're just pulling as an educated guess mid-span around our relative roughness value on the Moody diagram, I get a velocity of 9.90 meters per second, which I can then plug into my Reynolds number. What are we going to get? 9.90 meters per second times our diameter all over the kinematic viscosity that I pulled out of Appendix A, which is 10 to the minus 6 meters per second, meters squared per second. And we now have a Reynolds number of around 4.96 times 10 to the 6th, okay? So we can use that to get another friction factor, and we're just doing this circular thing until we iterate to a final velocity value. And this purple line is still here for my relative roughness, but we've got 4.6 for that Reynolds number, and that brings me way down here, well, way down, to 0.012, because that's 11345, right? So I can plug that back in, where I get a velocity of 10.74 meters per second, which then gives me a Reynolds number of 5.4 times 10 to the 6th, which going back up to my Moody diagram is still around here, which is still a friction factor of about 0.012. So we have convergence. Yay! So with the velocity value converged on 10.7 meters per second, I can multiply that to my area, pi over 4 times 0.5 meters squared, and get my flow rate, which is approximately 2.1 meters cubed per second. Now the head loss we've been doing up to this point, which is the loss due to friction along the length of the pipe, is considered a major loss. So what's a minor loss? Well, minor losses interrupt smooth flow due to mixing and eddies, which increase the losses. Minor losses are recoverable. So we talked about friction loss not being recoverable. Minor losses are. After we travel a certain length down the pipe, everything can come back to normal after the minor losses. These are described by a multiplying coefficient, KL, and you can find this in table 10.1 of your textbook. The minor losses become the major losses in short spans where we don't have that development length and we don't have anything to recover for those minor losses. So mini fittings, short span. The minor loss equation is going to be the sum of our K's times V squared over 2G. We're given 2 tanks, and the tank number 1 is filled with water at 20 degrees Celsius, and then the gate valve is open and the water flows through to tank number 2 at the bottom here through an 80 millimeter diameter cast iron pipe. Find the flow rate through the pipe. Starting with our energy equation, so if I set up the bottom of my pipe as my datum, okay, that's going to put U at 0 for being at my datum. There's no pressure in an open tank, no velocity in an open tank, no pumps, no turbines. The pressure head, okay, the pipe 2 is submerged. So I actually have 2 meters of pressure head above that pipe. Elevation 1 is going to be 15 meters. I don't have the velocity, which is what I'm trying to find for the flow rate. Head loss. Head loss, we're now talking about major and minor losses. So that's going to be my friction factor, length over diameter, V squared over 2G, plus the sum of all my KL values times the velocity head, V squared over 2G. Plugging in what I know to my head loss, I do not have a friction factor. My length of the pipe is horizontal 10 meters, vertical 12 meters, so that is 22 meters, all over 80 millimeters, 0.08 meters. I don't have my velocity over 2 times gravity. My K values from figure 10.10, a flush entrance is 0.5. A fully open gate valve is 0.19 from table 10.1, and a 90-degree elbow is 0.9 from table 10.1, and this is all times my velocity head that I don't have. Plugging this all back into my energy equation and solving for velocity. So I get velocity in terms of friction factor again. So this is exactly what we had with that last example, only this time we have minor losses included. So that means I need to make an educated guess on my friction factor based on my relative roughness. So my relative roughness for cast iron is 0.26 millimeters divided by my diameter, 0.12325. So I'm going to come up to my Moody diagram. My value is going to be somewhere in here. So I'm going to start with a guess of 0.03 because it starts to get real tight and narrow here with a smaller Reynolds number. And I'm kind of hoping for the larger Reynolds number size. So that's what I'm going to start with. That gets me a velocity of 5.09 meters per second, which then in turn gives me a Reynolds number. And I'm using kinematic viscosity because I can find it in Appendix A, and that's one less number I have to plug into my Reynolds number. And I'm using a mu of 10 to the negative 6 meters squared per second. I have a Reynolds number of 4.07 times 10 to the 5th. So going back to the Moody diagram, around here, can't draw a straight line. So about 0.026, which in turn leads to a velocity of 5.4 meters per second, which in turn leads us to a Reynolds number of 4.32 times 10 to the 5th. And on the Moody diagram, okay, even with my terrible drawing, that's still really close to where we were. So I'm going to call that convergence. And that gives me a flow rate of 0.027 meters cubed per second through that pipe from tank 1 to tank 2.